What is entropy? I think many viewers of my channel have encountered this term in one way or another, but I bet that most of you will find it difficult to explain what it means right off the bat. Entropy is often described as a measure of disorder or something like that. While there is some good sense in this intuitive definition of entropy, it is generally incorrect. The term entropy is found in many disciplines, including information theory, mathematical statistics, and even philosophy and psychology. But we will talk about entropy in the sense in which the term is used in physics, and in particular, in connection with the second beginning of thermodynamics, which states that the entropy of an isolated thermodynamic system cannot decrease. The most well-known household consequence of this principle is the impossibility of directly heating a hotter body by transferring heat to it from a colder one. In fact, this principle has a much broader meaning, but we will talk about it in detail a little later. And now, let's understand what entropy is from the physical thermodynamic point of view, and why the value of this very entropy is not supposed to decrease. By the way, if you like what is happening on our channel, I will be very happy if you become our sponsor here on YouTube. The more people who support the channel, the more time I can devote to it, and the more videos, the better quality I can make for my esteemed viewers. And here we go. In general, the concept of entropy was first invented by German physicist Rudolf Clausius when he studied the so-called isothermal processes. That is, processes in which the energy of the system seems to change, but its temperature remains unchanged. Let's imagine such a classical situation. There is a pot of water on the stove, hermetically sealed with a lid. That is not even a pot, but something like a pressure cooker. At first, the water in the pressure cooker will be heated. That is, its temperature will rise. At a certain stage, the water will boil, and its temperature will no longer change. The fire under the pressure cooker continues to burn, it continues to receive heat energy, but this does not lead to any visible changes, because the only parameter available to our direct observation, that is, temperature, remains constant. The question is, where does the heat energy go? We know that the energy is actually spent on the transformation of liquid into vapor. At evaporation, or rather the formation of liquids are cooled, and at intensive vaporization from the entire volume of the liquid, which we still call boiling, the formation spends all the heat supplied to the liquid without a residue. This is actually why its temperature does not change during boiling. But how to describe this case mathematically? What physical characteristic of the system of molecules, some of which are in the liquid and some of which are vapor above the surface of this liquid, changes during the heating process? At that time in thermodynamics, nothing like this existed, and Clausius had to invent this characteristic, and that's what he called entropy. So entropy, according to Clausius, is such a value of change which is equal to the amount of heat in the reported system divided by the temperature of this very system. That is, entropy itself will be written in this way. The same thing can be rewritten in another way using other equations of thermodynamics, like this, where U is the internal energy of the system, and P and V are its pressure and volume respectively. In other words, the heat that the stove gives to the pot of water goes to increase its entropy. And before the water boiled, that is, when the temperature of the water was increasing, and when it boiled and began to evaporate at a constant temperature, and then when all the water turns into vapor, and now this vapor, when further heated, will also begin to heat up, increasing its temperature and pressure. The development and course of many thermodynamic processes turned out to be more convenient to analyze by calculating how the entropy of the system changes during them, due to which entropy became the most important tool of thermodynamics. But another thing turned out to be even more important. Having generalized the data of sets in various experiments and observations, Clausius came to the conclusion that the entropy of a closed system cannot decrease. It must either remain constant or increase. Knowing this fact allows us to predict exactly how certain thermodynamic processes will develop. For example, we can expect that when water is heated in a pot, the water will evaporate until it boils away completely, but we do not have to expect that the empty pot standing on a switched-off stove will condense the water vapor contained in it from the air. The Clausius approach, without exaggeration, opened a new era in thermodynamics, but it had two major problems. First, it does little to help us understand what this very entropy is, shall we say, on our fingers. And secondly, within its framework, it remains unclear why, in fact, the entropy of a closed system cannot decrease. The real physical meaning of the concept of entropy was later revealed in his works by another famous physicist, Ludwig Boltzmann, who translated this term from thermodynamic to molecular statistical language, obtaining this expression, where omega is the so-called statistical weight of a given state of matter, K is Boltzmann's constant, which plays the role of the proportionality coefficient between temperature and energy. For example, the average kinetic energy of the molecules of an ideal gas is proportional to the product of the Boltzmann constant by the temperature of this gas. In the simplest case, when the molecules are material points, the exact formula would look like this. With the Boltzmann constant, I hope it's clear, but what is this statistical weight of the state, which we have labeled with the letter omega? The strict definition sounds like this. It is the number of microscopic states, with the help of which a given macroscopic state can be composed. I realize that it doesn't sound too clear either, so I'll try to explain this matter with a simple example. Let's take a handful of dice and roll them. The set of values that fell out on each of the dice will be an analog of a microstate, and the sum of these values will be a macrostate. Obviously, there are many variants of dice falling out, giving this or that sum result, and the number of such variants will be different for different results. For example, if there are 2 cubes, then there is only one variant of falling out the results, 2 and 12, that is, only one microstate for each of these macrostates, and the entropy of macrostates 2 and 12 will be 0. Macrostates 5 and 9 can be realized in 4 different ways each. That is, the entropy of such macrostates will be equal to 1.4 Boltzmann constants. Finally, there are 6 ways to throw away the result 7 on 2 cubes. The entropy of such a macrostate will be 1.8, and this will be the maximum possible entropy of such a system. It is easy to see that the more ways we can get this or that result, that is the greater the statistical weight of this macrostate and its entropy, the greater the probability that as a result of a random throw, we will get this very result. Indeed, the probability of falling on 2 dice of 12 or 2 will be equal to 1.36 or approximately 3%. The probability of rolling a 5 or 9 would be approximately 11%, and the probability of rolling a 7 would be 17%. There is even a formula in mathematical statistics that statistical weight and probability are directly proportional to each other. Hence, a very important conclusion follows. The macrostate with the highest entropy is at the same time the most probable state of the system. That is, the greater the entropy of a given macro state, the more likely it is that we will find the system in this particular state by random observation. Molecular physics, of course, does not work with dice. It deals with molecules. However, it is not difficult to make a clear transition between the former and the latter. For example, let us imagine a molecule located inside a certain narrow box. Let us conditionally divide the box into 6 parts, and taking into account the fact that all molecules are in a state of incessant and chaotic thermal motion, we can conclude that the probability of finding the molecule at a given moment in one or another cell of the box will be approximately the same, just as if its position were determined by the result of throwing a 6-sided die. We can also compose a more complex system of several such boxes, and the evolution of such a system can be modeled by rolling several dice. The only thing that would make sense for us to change would be the definition of the concept of the macrostate of such a system. The sum of results on the dice at such approach will not have any physical sense anymore, but the arithmetic mean of such a result will have such a physical meaning. In essence, it will be nothing else than the position of the center of mass of this system. From our analogy with dice, it is not difficult to understand that the greatest entropy of our system will be observed in situations when the center of mass of the systems will be located approximately in the middle. That is, the molecules will be distributed throughout the system from left to right, approximately evenly, and these same states of this system will be the most probable. Yes, there will be possible low entropy situations when the distribution will be non-uniform. For example, all molecules will gather to the right or to the left, or they will line up along one of the walls of the boxes. However, such situations will occur quite rarely, and the less often, the more molecules will be in our system. But suppose that such a low entropy situation does occur. That is, looking at our system at some point in time, we will see that all the molecules have gathered, say, in the left half of the box. Let's try to predict how the state of the system will change in the future. Suppose there are only 10 molecules in our box. In this case, the probability that at the next moment of time we will find the center of mass of the system shifted towards the geometric center is about 80%. With a probability of about 15%, the center of mass will, on the contrary, shift to the left, and with a probability of 5%, it will remain in place. That is, most likely the center of mass will shift to the right towards the geometric center, that is, to the place where the system will have more entropy. And the more particles there are in the system, the more likely it is that events will develop in this way. It is not a fact that at the next moment of time, the center of mass will be exactly in the geometrical center. It can both not reach there and fly further, having appeared to the right of this center. In the latter case, we, having seen that our system has appeared in such a state, will be able to state that most likely at the next observation, we will see that the center of mass will move, on the contrary, to the left. But if during one of our observations we see the system in a macro state, with the center of mass in the geometrical center of the system, that is, in the state with the highest entropy, then it will be difficult for us to make any predictions concerning its further evolution. Yes, with a certain probability the center of the system will remain there, but with a higher probability it will shift to the right or to the left, and the probability of displacement in both directions will be the same. And what is most interesting is that, having undergone such a shift, the system will most likely evolve in the future to return to a uniform distribution of molecules across the width of the box. In real life, in the vast majority of cases, we cannot track the position of individual molecules, but can only record the macroscopic parameters of the system, in our case, the position of its center of mass. And so, observing this position, and knowing nothing about the behavior of molecules, we can come to an unexpected conclusion. The center of mass somehow seems to be attracted to the geometrical center of the system, as if there were some force pulling it there, to the position, which, let me remind you, is characterized by the highest entropy of systems. We know, of course, that there are no such forces. Molecules are not affected by anything, and they move inside the box completely randomly. That is, the occurrence of this or that microstate is equally probable. However, it is this equiprobability multiplied by the independence of the molecule's motion from each other that gives rise to certain statistical regularities in the evolution of the system. Namely, it's striving to be in the most probable state of uniform distribution, which is at the same time the state with the highest entropy, as well as the equilibrium state of the system. That is, the state in which it will have no clear tendency to evolve in one direction or another. This, of course, will not mean that having found itself in such a state, the system will remain in it forever. As we have seen above, there will always be a possibility that the system will spontaneously escape from such a state. However, whenever this happens, there will be the same statistical force in the system that tends to bring it back. Such random deviations from the equilibrium state in complex systems obeying the laws of statistics are called fluctuations. It is theoretically possible that as a result of fluctuations, the state of the whole system will change. Say all the gas will shift to one part of the vessel. However, small fluctuations are more common. When deviation from uniform distribution in one or another direction is observed only in some small parts of the system, and they involve only a relatively small number of molecules. That is, on average, these molecules are distributed more or less uniformly throughout the system. But in some points of the system there is an increased or decreased concentration of them. In this case, of course, there will always be a probability that in practice the system taken out of equilibrium evolves not in the most probable direction of the state with high entropy, but in the opposite direction. However, the more particles there will be in the system, the less probable such evolution will be. And if something like this does happen, the statistical laws will immediately try to return the system to an equilibrium state, or at least toward that equilibrium state. That is why, observing the evolution of real thermodynamic systems consisting of trillions of molecules, we may well come to the conclusion about the existence of the principle of non-reduction of entropy, as a consequence of the simple fact that the states with the highest entropy are simultaneously the most probable. However, everything we have mentioned above concerned the Boltzmann definition of entropy. The law of non-decreasing entropy, as we remember, was introduced by Clausius, who defined entropy differently. Fortunately, it is not difficult to show that one definition of entropy follows from the other. To do this, consider our box of gas. Let there first be one single molecule in the box. The probability of finding it at a given time in some particular part of the box with volume V1 will, as is easy to understand, be equal to the ratio of this volume to the total volume of the box. If there are n independently moving particles in the box, then each of them can be in this volume V1 with the same probability. And the probability that all of them will be in this volume at the same time will be equal to V1 divided by V to the degree n, since the probability of coincidence of independent events is equal to the product of the probability of occurrence of each of them. Suppose this does happen, and all our molecules have at some point in time assembled in the volume V1. This state will definitely be non-equilibrium, and we can be practically sure that at the next moment of time, these molecules will start flying in different directions, filling more and more volume. Let them occupy the volume V2 after some time interval. The probability of occurrence of such a situation obviously will be equal to V2 divided by V to degree n, and the ratio of probability P1 and P2 will be equal to this thing. We know what happens to a gas when it expands. It cools. The magnitude of the change in thermal energy of a gas as it expands can be calculated using a formula like this. Now let's substitute this expression into the formula for Clausius entropy. To calculate the change of entropy during the transition from the volume V1 to V2, we take from this expression the integral over the volume from V1 to V2, obtaining this expression, which can be rewritten in this form. But the ratio of V2 to V1 in degree n, as we have seen earlier, is equal to the ratio of probabilities of occurrence of such states, whence our formula can be rewritten like this. All we have to do now is to remember that the probability and statistical weight of a state are directly proportional. That's it. We express the ratio of probabilities through the ratio of statistical weights. Substitute this case into the formula, remember that the logarithm of the private is equal to the difference of logarithms, and get an expression in which it is easy to recognize the Boltzmann definition of entropy. Which means that everything we have said for Boltzmann entropy will also work for the Clausius thermodynamic approach. Having made sure of this, let us continue studying the essence of entropy and try to understand how the impossibility to heat a hotter body from a colder one follows from the law of its non-decreasing. We know that temperature is nothing else than the average kinetic energy of thermal motion of molecules of matter. Simply put, in a hot substance, say in a hot gas, there will be more fast-moving molecules and fewer slow-moving ones, and in a cold one, respectively, vice versa. Let's designate fast and slow molecules by different colors just to make it easier to observe them. In a gas, all molecules move independently of each other and do not interact in any way. Therefore, we can consider separately from each other fast and slow molecules of each of the substances, hot and cold. If we now consider the ensemble of fast and slow molecules as two different gases, we can easily see a very simple thing. The distribution in the volume of both is initially unequal, and we can predict how these molecules are likely to behave over time. Obeying the second principle of thermodynamics, they will tend to distribute themselves in the vessel to the state with higher entropy, that is, more uniformly. Let's say it's like this. Now, let's remember that we actually have one vessel, and both fast and slow molecules make up the same substance. So let's put the two ensembles back together. We'll see that the tendency of the systems to reach an equilibrium state has resulted in less fast molecules and more slow molecules in the hot gas. That is, the average velocity, and therefore the average kinetic energy of its molecules has decreased, which, in the language of thermodynamics, means that the body has cooled down. In the cold one, on the contrary, there are more fast and less slow molecules. That is, this second volume of gas has heated up. Is this the only possible outcome? Of course not. We are considering a random probabilistic process, and among other things, there is a non-zero probability that some of the hot molecules from the cold body will move to the hotter one, and some of the cold ones from the hot one to the cold one. That is, the hot body will get even hotter, and the cold one will cool down additionally. Exists? Then such a probability exists. However, in real molecular systems consisting of a huge number of particles, it will be negligibly small, and even if such a situation occurs, then, as we have seen above, it is likely to be very fleeting and will exist only for a negligible moment, so negligible that we may not even notice it. This is, of course, only an approximate description of heat conduction processes in bodies, not quite appropriate even for gases, and certainly not working in liquids and solids. The point is that in molecular physics, the microstates forming a given macrostate are determined not only by the position of molecules, but also by their velocity, more precisely by their momentum and kinetic energy. The position of each particular molecule at each moment of time is thus no longer random, but is determined in a certain way by the value of its velocity and coordinate at that moment of time. However, in the course of their thermal motion, molecules constantly collide with the walls of the vessel and other molecules, as a result of which both the direction and even the magnitude of their velocity are constantly changing. In real systems consisting of a huge number of molecules, it is practically impossible to trace any regularities of such changes. Therefore, these changes look quite random, and the reasoning we used above about the probabilistic nature of molecular motion remains quite viable. Nevertheless, it is still necessary to take into account the presence of velocity in molecules. In particular, microstates, in which these molecules are in the same positions but have different velocities, are different microstates from the point of view of molecular physics. And such different microstates can form different macrostates. That is why, in fact, the entropy of a substance increases with heating. So now we can try to formulate what entropy really is. In fact, it can be called a measure of how close a system is to its equilibrium state under given conditions, that is, to the state in which it will not be inclined to evolve in one or another particular direction and will undergo only fluctuations, random deviations from the equilibrium value. For a system of non-interacting particles, as we have seen above, this state will correspond to a uniform distribution of particles in the system. And it is with this understanding of entropy that the widespread opinion that entropy is a measure of disorder is apparently connected. Indeed, we have seen above that in states with high entropy, the particles are distributed uniformly and without any system. Conversely, states in which the distribution of particles is at least somehow ordered, say they are all in one part of the vessel, are characterized by significantly lower values of entropy. The process of entropy increase in such systems can, indeed, look like the disappearance of order and the reign of chaos. However, so far we have considered only systems of non-interacting particles whose evolution was purely random. For such systems, the equilibrium state is indeed simultaneously a state with uniform distribution. In real physical systems, their components always interact with each other in one way or another, at least by means of gravitation. And now we should include in our consideration also the interaction between particles. The behavior of these particles will depend also on each other and on external factors. Their positions will no longer be determined by mere chance, and the equilibrium state will no longer be synonymous with uniform distribution. For example, gas molecules in the Earth's atmosphere, which are in the Earth's gravitational field, turn out to be unevenly distributed because their concentration decreases as they move away from the Earth. Such a state turns out to be more ordered than a simple, uniform distribution. Nevertheless, it is the equilibrium state for the Earth's atmosphere in the Earth's gravitational field. One more example. Let us imagine a certain vessel containing a mixture of air and water vapor. Sharp cooling of the vessel will lead to condensation of the vapor into a liquid. That is, the water molecules that are randomly and evenly distributed throughout the vessel will condense into small droplets, which will then collect into larger droplets and eventually coalesce into one large drop. Such a system looks already much more ordered and less chaotic, and one may even get the impression that the entropy of the system has decreased as a result, which seems to contradict the principle of non-decreasing entropy. In fact, there is no contradiction. Although if we consider entropy only for water molecules, it will indeed decrease in the process. However, it is known that during condensation of liquid, thermal energy is released, which in this case will be transferred to air molecules inside the vessel. The thermal energy of the gas inside the vessel will eventually increase after all the processes are completed, and we remember that an increase in thermal energy means an increase in entropy, and if we carefully calculate everything, it turns out that the total entropy of the whole system, that is, air and liquid, will eventually increase, despite the fact that at first glance the system after condensation looks more orderly and less chaotic. This is why systems with high entropy are far from being highly disordered, and a certain orderliness can be observed in them, in case this is the orderliness that corresponds to the equilibrium state of the systems. Another good way to visualize what entropy is to think of it as the degree of energy distribution within a system. For example, the internal energy of a gas is equal to the sum of the kinetic energies of the molecules that make up the gas. In the case of a low entropy state, when the gas is concentrated mainly in one part of the vessel, its internal energy is also concentrated there. Its concentration in this part of the vessel will be large, while in other parts of the vessel the energy density will be insignificant. And if we observe the evolution of such a system, we will see that it will gradually move to a state with higher entropy, and this state will be characterized by a more uniform distribution of both particles and their energy, and hence the internal energy of the gas as a whole. This approach allows us to extend the concept of entropy and use it to analyze and predict the behavior of systems beyond thermodynamics and molecular physics. For example, let us imagine a ball lying on the top of a hill. Due to its position, this ball has some potential energy, which is concentrated in a small region near its center of mass. Suppose that, as a result of some reasons, the ball rolled down the hill, in the process of which its potential energy changed into kinetic energy, which is still concentrated inside the ball. But as the ball rolls, its kinetic energy will gradually be transferred to the surrounding environment, such as air or earth, through friction, which will cause them to heat up, increase their thermal energy. In other words, the potential energy of the ball first transferred into its kinetic energy and then distributed in space in the form of thermal energy. Its distribution became more uniform, which means that the entropy of the whole system as a whole increased. And since we know that the entropy of systems tends to increase, or at least does not tend to decrease, we would not be very surprised to see a ball rolling down a hill. However, we will definitely be surprised to observe the reverse process when a ball lying on the hillside suddenly rolls of its own free will to the top of the hill. Again, this is not impossible. There is some probability that at some point in time, the velocities of all the molecules of the ball will be such that it will roll to the top of the hill. In fact, it will be a fluctuation, but a fluctuation of such gigantic scales that we are unlikely to observe it, even if we look at the ball all the time of the existence of the universe. However, in life, we often face situations when entropy of this or that system seems to decrease. A classic example is an ordinary refrigerator that cools air inside its chamber and heats it outside. Of course, this process leads to non-uniform distribution of energy and sort of entropy decrease. However, as in the case with condensation of water, we are talking about change of entropy of only a part of the system. A refrigerator does not cool the air spontaneously, but only when we supply it with electricity, which has to be produced first. Let for our refrigerator, it is produced by some electric generator, in the process burning fuel, which is in fact a reservoir of highly concentrated chemical energy, that is, a reservoir of low entropy. First, this fuel is burned, during which chemical energy is converted to thermal energy, leading to an increase in entropy. Next, thermal energy is converted into mechanical energy of movement of parts of the generator, and then this mechanical energy is converted into electrical energy, which powers our refrigerator. Each stage of energy conversion from one type of energy to another is accompanied by losses. Part of the energy is released into the environment, which leads to a decrease in the concentration of energy and consequently to an increase in entropy. And only at the last stage inside the refrigerator there is some entropy reduction. Moreover, this decrease will be less than its increase in the whole process as a whole. Although entropy has decreased in some part of the system, it has increased in the whole system. And moreover, sooner or later, the fuel in the generator will run out. Energy production will stop, and the refrigerator will stop working, and the temperature difference created by it will decrease. Entropy will increase, and finally, the change of entropy for the whole time will be positive both in the whole system as a whole and even in some specific parts of it. And this is a very important conclusion. Any process of entropy decrease we observe, even locally and briefly, almost always corresponds, except for fluctuations, to some larger process of entropy increase, the process of transition of some larger system to an equilibrium state with uniform energy distribution. And this statement is true both for some individual systems and for the universe as a whole. By and large, all the processes taking place in the universe, be it the Big Bang, the formation of stars and galaxies, the formation of planets and the evolution of life on them, are in fact private manifestations of the gradual increase of universal entropy. It was this consideration that led the same Clausius to the concept of the so-called heat death of the universe. Sooner or later, this universe, being a closed system, will reach an equilibrium state with maximum entropy, after which any physical processes in it will cease. Clausius was, of course, dramatizing. Even our level of understanding of entropy already allows us to realize that final heat death for a large system, like the universe, is impossible. Indeed, we have already said that even being in an equilibrium state, the system still continues to generate fluctuations that are deviations from the equilibrium state. And even if these fluctuations will be relatively small and short-lived on the scale of such a system as the universe, they may well have the scale of entire galaxies and exist, gradually returning to the equilibrium position for billions of years. And in general, who knows if the universe observed by us and its evolution is not more than some local fluctuation of some much larger meta-universe. And all physics known to us is no more than a process of gradual return of this fluctuation to the initial equilibrium state. However, this is already reasoning rather from the field of philosophy than physics. What is important for us is that, having understood the concept of entropy, we have got a powerful tool with the help of which we can effectively analyze both qualitatively and quantitatively the development of many physical processes. And that's all for today, dear friends. Have a good day. Thank you very much for your attention and see you soon.